Hello. We have all the pieces in place now for doing our model matching in our three-dimensional point cloud. We've got a way to capture that point cloud data and a way of extracting some planes from it. And we've also got a way of representing the kinds of objects that we're looking for in terms of a set of planar patches, effectively polyhedra. What we're going to look at now is that kind of the process of matching all those objects together and extracting the pose and verification. So the question that we started with really is there a wedge in this scene? Okay, and here's the plane data that we know something about, and we've got our model right here, and we want to say, well, you know, is that in there? And what we're going to need to do is somehow match up the surfaces from this with the surfaces that we found in the data. Fortunately, we've got lots of a priori knowledge, okay, about all of these different objects, and we also know something about the geometric transformations which can map this data, this model onto the data. This is the main sort of sequence or the main pipeline that we're going to work with through here. So we've got our segmentation, and what we're going to look at next is the model matching algorithm, very briefly, where we take the planes and the geometric model, and that's going to give us a set of correspondences between the planes and the model planes and the data planes. Just like in the two-dimensional case where we got a set of correspondences between the two-dimensional lines from the image and the two-dimensional lines from the model. With that case, once we had the lines matched, we could then do pose estimation. We're going to do exactly the same thing here in the three-dimensional case. We're going to take our three-dimensional matched planes and we're going to estimate the pose of the object that maps the model onto the data. Once we've done that, we can do some kind of a verification process. And if there's some sort of failure of that, like maybe we've got some false hypotheses or bad matches or something like that, that verification won't work. The model planes will not lie on top of the data planes. And so therefore we're going to have to go back to the backtracking into the model matching algorithm and sort of try it again and keep going through until we get a good match, or alternatively say that there's nothing that matches right here. And once we do get that good match, we'll also get the pose or the translation and rotation that matches, that maps the model onto the range data. So we're going to look at the model matching next. And in fact, we're not going to look very much at that model matching. In this particular case, we're going to use the interpretation tree just like we did with the two-dimensional case. It's going to use exactly the same code. What's going to be different here is the set of constraints that we're going to use. Okay, and previously we used a unary constraint that was based on length, and here we're going to use one that's based on surface area. Previously we used a binary constraint that was based on the angle between the lines. Here we're going to use the angle between vectors, in this particular case the surface normals. And that's all we really need. One could add an additional constraint, like a trinary constraint that looks at 3 consecutive matches. And an example of a kind of trinary constraint would be the sign of the vector triple product right here. So if these were the 3 surface normals, you could look at the sign where there's positive or negative on this. Well, we don't really need to use that constraint here as well. And the net result of, after substituting these different binary and unary constraints into the interpretation tree algorithm and running our data through it, what we get is a set of paired model and data lines, or planes, just like we did with the data lines in 2 dimensions. And this is the kind of result that we would get out, and it does work quite effectively. And here's our model with our model surface 1, 2, and 3, and our data surfaces 1, 2, and 3. And this is an example of the match that you might get. Now, of course, this is a full 3-dimensional object, and so you might get additional matches, you know, with the object sort of flipped over, it would still match with this data right here. But this is one particular match that we can look at. Okay, so this is really just quite a straightforward extension of the 2-dimensional interpretation tree matching algorithm into 3 dimensions. And all we really needed to do for that really was just to replace our 2-dimensional type of constraints with a 3-dimensional constraints, and then think about how to do this in 3-dimensional coordinates rather than in 2-dimensional coordinates. Thank you.